let's start simple. I have a problem, right? I'm starving for pizza. I'm really, really hungry, but I'm quite stupid. I don't remember a lot of things. I don't remember how to have pizza, okay? So you tell me, you give me a sequence of actions that will let me end up happy, okay, with my pizza eating, okay? So what do I do? So I start hungry, what do I do now? Decide to make pizza, okay. So, okay. Make pizza. Okay, I'll just, okay. This is a stove and an oven, okay. So make pizza. Okay, after I make pizza, what do I do? That's a simple recipe, right? Okay. Let's make it more interesting. Okay, I have my pizza. I come from the same country as Giotto, and it shows. So I eat one slice. Okay. I eat 2 slices. I eat 3 slices. And then I'm really happy. I want to give a name to these transitions. So, okay. This is like me eating pizza. It's a slice of pizza in my mouth. Okay. Another one, and another one. Okay. Can you give me another way to solve this problem? So we have 2 paths. Okay, that's a nice idea. That's exactly what I would do. Because I'm not good at cooking. So let's do a phone. A takeaway home. So just this is an order to the takeaway. Okay, and then well, the takeaway comes. So I put a motorcycle. Okay. And then, okay, I get my pizza, I eat, I'm happy. Okay? So this diagram shows the structure of my problem, okay? So it is a very specific problem. It could be uninteresting, but I have a way of expressing this problem. And actually, expressing it like this, so me eating the pizza, okay? You have a set of states. So when I'm in the state, I'm hungry, I've ordered, I have my pizza, eat 1, 2, eat 3, happy, okay? So the system has a set of states and a set of transitions. So I can get from one state to the other by doing something, okay? This is a really general way to think about problems, okay? Many systems can be modeled this way. For example, in this moment I'm working on a neural network, so we're talking about biology, and I recently discovered that this neural network has the computational properties of this neural network have exactly this structure. So this structure has a name, and these diagrams are called DFAs, deterministic finite state machines. So the name, finite states, you have a finite number of states. Deterministic is because from one state, if you do one action, you always end up to a certain state. You will never end up somewhere else. Okay, it's not probabilistic, it's deterministic. So if you're in one state, you do one action, you end up in another state. And it's always that state. We can abstract away. Didn't really write it properly. Abstract away details. So we can abstract away all the fancy drawings, all the fantastic drawings I made, and we can get to the real structure, okay, the bones, the skeleton of the problem. So the skeleton of the problem, we can give numbers to the states instead of drawing them. So one state I'm hungry, I have to copy it. I don't remember the instructions. Let's say 2. Let's say 3, 4, 5, 6, 7, 8, 7, 8, 1, 2, 3, 4, 1, 2, 3, 4. I think this is okay. The state in which I'm happy, we will denote him. We will denote it with a double circle. Okay. So this is when you have a DFA. If you have a state with a circle inside, it's called an accept state. It means that if you reach that, then you're kind of happy. Now I will specify all of this. Okay. So this is a set of states. Okay. Really anonymous, and we have transitions, right? So instead of a fork here, we can have some F. Instead of OK, we can have some O. Instead of eating, we add E, and then E, and then E, and then E for eats. And instead of phone, we put a P. Instead of motorbike, we put an M. Okay, this is the bone of my problem. So we have an initial state, which is this one. And then we have transitions, and then we have states. And if we do the right things, if we get the right transitions, we end up in an accept state. Okay? So now that we have that, you can observe how getting to the skeleton of the problem makes the problem unspecific. So this is, you remember what I told you, that computation is symbol manipulation without meaning. You don't have meaning in the symbol manipulation. You just have symbols and structure as syntax, okay? So this is really nice to have, because now you can implement your own meaning. So you have a skeleton of an abstract problem, and you can give your own meaning. For example, let's see. You want to buy 4 flowers for your girlfriend. Okay? So E is getting the flower. Maybe here you go to the shop, you pay, or you phone the shop and they get you the flowers. Okay? It's the same structure, different problem. And you have many other problems that have the same structure. This is really nice to have. That's why we symbolize, we get the skeleton out of the problem by abstracting away all the details. And this abstraction is called, this particular abstraction is called DFA, as I told you, okay? So mathematically, let's try to give a better definition, okay? A formal definition of this object. So it has a set of states. These states, you know about set notation, right? What a set is. Do you know what a set is? So a set is a collection of anything, okay? And the set notation is something like that. So, for example, if we talk about a set of states, Q is a set of state, and Q is equal to collection of things. In this case, states, which is 1, 2, 2, 8, I think. Was it 8? Okay. Okay, then you have to... something was wrong. So you have to establish an input alphabet, right? This one. So your input alphabet is the set of actions you can perform, okay? In this case, we have F, O, E, M, E, E, E. So it's a set, so again, a collection. F, O, E, M, P. And maybe, I don't know, Z, A, I don't know. They're not used, but they can be part of the alphabet, okay? So, as I told you, you have to establish an initial state, okay? So, where's your system in the beginning? And we just say, in this case, state 1. So this means, this means the initial state is some state belonging to the set of states, and this state is state 1. Okay, is it clear? More or less. Okay. Then you have a set of accept states. In this case, the only accept state is state 8. Okay. It is a set which has only one element. Okay. And then a transition function. So you have your symbols, your actions, the actions you can do. You have your states. You have to put them together. Okay. So the transition function tells you, okay, I'm in state 1. What actions can I perform? I can have, I don't know, F. Okay, if you're state 1 and you have an F, you go to state 2. Okay, this is the transition function and can be expressed as a table. So you have 1, 2, 3, 4, 5, 5, 6, 8. Okay, and then you have, don't remember, F-O-E-M-E. Okay? And this is just a table. So you're in state 1, you receive an F, you end up in. Where do you end up?
3.
Okay? Is it clear for everybody? You're in state, I don't know, let's say 4, and you have M. Where do you end up? Nowhere. There's no transition. So this function can be partial. Okay, it doesn't have to be defined for every state and every input. Some inputs can just not be there. Okay. So for was it M? We denote it like this, or just slash. Okay. So you have a table. This is nice because it means that if you want to have this in a software, the only thing you need to do is program a lookup table. Okay? And there's a lot of problems that can be solved by lookup tables. And lookup tables are nice because you can access them very quickly. You don't have to do a lot of computation. It's just looking up. And actually, you see lookup tables everywhere. If you have very well-defined problems that just accept fixed state of answer solutions, okay? So this is a DFA. Okay, oh yeah. Just to have the mathematics clear, that's delta function. So the delta function is the function saying, okay, I'm in a state, I receive an input, where do I end up in another state? Okay. You can extend that to strings. I will tell you now what a string is, but a string is just a collection of symbols, positionally meaningful. Okay. So you can extend that to strings using it's called an inductive definition, meaning that you have a base case. You define an inductive case, and if you actually do the math here, you can see that you end up in the end by recursively applying this definition with just a delta function which looks something like that. So delta, for example, of delta of, I don't know, Q1, some symbol, okay? Something like that. So you have, from this, you can get the object that you already know, the delta function, the simple one, okay? Okay. Oh, well, sorry. Okay, so we have a problem. I want to write down the solution. Actually, I want to write down the solution. So the solution here is a set of symbols, right? I call it L. So the set is phone, bike, motor, eat. Actually, no, why I put the comma. Okay, this is a solution to our problem. Then we have another one, which is fork, okay, eat. Fork, okay, eat. Okay? This is our set of solutions, the solutions to our problem. I already told you. So these are just symbols, right? And this takes us to the language metaphor, okay? Well, okay, before I want to talk about problems. What's a problem? What do you think a problem is? If I ask you to give me just a definition of problem, you can give yours.
It's just a task, I guess, you want to complete.
Mm-hmm. Okay, what are the parts? Okay.
It's changing something, I guess.
Or problem. So you can think about a problem just as a mapping between an input and an output, right? Whatever problem you can think about, you can always find an input and an output. For example, if I ask you to, well, exactly, if I ask you to tell me how to get a pizza, this is an input, I'm asking you, and you give me an output, and that solves the problem, right? So here are examples of problems. So, for example, how would you solve the first one? If this is my input, what will be the next fish? I'm keeping score. You have to tell me the answer.
A smaller fish.
Ah, you're really smart. Smaller fish. What's brown and sticky? Of course. That's older than the universe itself. Stick. But also Nutella. And I won't go farther. What numbers are even? It's easy, okay? 2, 4, 5, 6, blah, 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 okay? It turns out, okay, you can express every problem like that. Some input and output, it's a function, okay? If you've studied a little bit of mathematics, a function is exactly that. You give me some input, and I tell you the output, and that's a function, okay? It turns out that every problem can be mapped to a more fundamental problem, okay? In this case, our set of inputs and outputs are unbounded, okay? But I can do that and find, so what is called as a decision problem, okay? What's a decision problem? Instead of having whatever input I want, whatever output I want, I just have whatever input I want, mapping to an answer, a digital answer, yes or not. And every problem can be expressed as a decision problem, and I will show you simply how. For example, in this case, this is not a decision problem, but if I tell you, okay, if I tell you, is this fish the solution to this chain? And you map back, yes, no, okay? And you can do it with whatever, whatever other fish or input, okay? If I tell you, is Nutella, this you can substitute brown and sticky? Yes, no, decision problem. Okay? Have I convinced you? Are you convinced that every problem can be mapped back to a decision problem? Say yes. Yes. I did it, okay. What numbers are even? Is 2 even? Is 4? Is 5? Okay? So you can have a mapping that says, no, this is a decision problem. Okay? So why are decision problems interesting? Because decision problems mapping the correct solution to your problem to a yes and the incorrect ones to a no, you can find structure in your solutions. So there are some problems that have a peculiar structure that can be dealt with effectively. Meaning that for some problems, you can, I'll show you. Okay. First, I want to talk about the language metaphor, okay? So when we talk about problems, decision problems, we end up with the concept of language, meaning the set of strings that map to yes, okay? So the set of strings that are a solution to my original problem, okay? So, for example, if the problem is what numbers are even, okay? Then the language will be 2, 4, 6, 8. If the problem is what's brown and sticky, then you have stick, Nutella. So you build a metaphor, okay? The metaphor of the solutions of your problem being a language. You can express a solution to your problem using a language. So what's a language? Okay. First, an alphabet is a set of symbols. Okay. So it can be really everything. So it can be 0 and 1. Very often it's 0 and 1. It can be phone, bike, blah, 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 what we saw before. So it doesn't really matter. So symbols are just placeholders, okay? They don't really matter. So let's say that our alphabet is A, B, C. This is again set notation, okay? So an alphabet is a set of symbols. It's a collection of placeholders, of symbols, okay? Now we define string. What's a string? A string is a collection, a concatenation of symbols, okay? I think it's pretty clear, right? You put a sequence of symbols, that's a string, okay? And what's this weird notation? So a string S belongs to clean star of alphabet. We will see this clean star later, okay? What does it mean? So this symbol here means all the possible strings, all the possible combinations of the symbols, okay? So for example, a string on this alphabet, sigma, so on ABC, could be A, could be B, could be AAC, could be BAC, okay? So all possible combinations. You have to, push it. So this string here is called the empty string. It is very useful, and it does exist. It's a string without symbol, so its length is 0. Okay, it's a concatenation of 0 symbols, and it is important. And if you get strings on an alphabet, the empty string is always a string on some alphabet. Okay? Now we come to the language. So the language is a subset of all the possible strings on an alphabet. Okay? So you get all the possible strings, you choose some, and you end up with an alphabet. An alphabet can be finite. So for example, in my last problem, the problem of the pizza, okay? The language was finite. You had 2 solutions, okay? Your language could be infinite. For example, what numbers are even? You have 2, 4, 6, you have an infinite number of even numbers. And that's an infinite language. But the important thing is that it is always a set of all possible strings from an alphabet. Turns out, okay, we can choose, for example, all strings that are made of A's. This is an infinite alphabet, okay? It turns out that there are different kinds of languages, okay? Languages with different structures. And each language has a certain machine that can understand it, that can accept it or reject it, that can solve the problem that the language is describing. For example, in my original problem, the one with pizza, and actually all problems that have a finite language, you can use a DFA, so a collection of states, a collection of, so an alphabet, a delta function telling you how to connect states and alphabet, okay? And it is really nice that many problems are actually quite simple. Okay? And the kind of problems that can be solved with DFAs are actually quite simple, meaning that they have a simple structure. But it is this structure I'm talking about. If you find out that your problem has these underlying structures, this underlying skeleton, you can solve it very efficiently with DFAs. And you have a lot of problems that you can solve with DFAs. DFAs are for example, used in compilers. Okay? In compilers, the first step of a compiler is the lexical analyzer, right? So you get your text. Your program is a piece of text, okay? And then you have to have some program, something that takes this text and finds out if there are keywords, okay? If there are special words, okay? And that's done using a lexical analyzer. So the lexical analyzer finds tokens, for example, a C program. If, okay, I found if, I found else, okay, found brackets, and this is done with DFAs, okay? The underlying structure of the problem of finding out if there are keywords in your program is a regular language. They're called regular languages. They are the languages describing the most simple problems, meaning that they can be solved using very, very simple machines. That's the ones I showed you, and I'll show you again. So, and first I want to make sure that we're on the same page with set theory, because we're going to use it quite a lot in this lecture, and actually in the end in the rest of the module. So, set theory notation. If L is a set, we can give a description of the set. Okay, that's how we build our set. Usually, a good way to describe the set, okay, it's like this. So, you say L is a set, it is a set, a collection of elements, where each element is such as, this is such as, if you want to read it out loud, this is such as. It's, you list its characteristics here. For example, the set of even numbers. L, I wrote it down so it's clear. L, each element of L, let's call the element X, it is such as X is equal to 2n, where n is a natural number, okay? This is the set of natural numbers, n belongs to natural numbers. Okay, this is the set of even numbers. Is it all clear for you? Is it? If it's not, you have to tell me, because you will have to deal with that on your test, and I want you all to pass your test. So if anybody has any doubts on this, tell me. I assume it's very clear. Okay, so this is the notation. So you say if X is an element of L, then it has some characteristics, okay? Now let's make some examples. So on sets, you have some important operations, okay? Meaning that you can combine sets, do things to sets, and get other sets, okay? And you probably know already these operations, but I want to make sure that we're on the same page. So let's give some. Okay, you tell me something to put into the set A, whatever. Give me a couple of elements of whatever set you're thinking of.
A and B.
Okay. No, it's all right. A and B. Okay, so what about B?
0 and 1.
Okay. Perfect. Okay, so they're finite sets. That's all right. And now we do the operation. So the union operation, what does it mean? That you get all the elements of one set, you get all the elements of the others, and you put them together in one set. If there's one element that is in both sets, there will be only one in the new set, okay? So that's it. This is the definition of A union B. The definition is, in A union B, you have each element belongs either to A or to B. Okay? One of the two. So in our case would be A, B, 0, 1. Is that clear? I think it is, right? Okay. Concatenation. Because we're dealing with the alphabet and strings, we have this operation, which is concatenation. The definition is every element of A, B, or A concatenated B. Normally there will be a dot here, but usually you just drop it and say A, B, okay? Because it's visually concatenation. So every element of AB is an element of the for XY, where X belongs to A, Y belongs to B. So help me out here. What are the elements of AB?
A0.
Okay. Go on. Wait. We have a problem here. No, 0. A0.
A0.
Yeah, sorry.
A1.
Okay.
A0. A1.
0, A1, and yeah, that's it. We have 4 elements. Okay. Some further notation. So this notation here is just eye candy, syntactic sugar. So if we have AA, you can just write A to the second. If we have A, you can write A to the third. In particular, with this eye sugar, yeah, and this eye candy, sorry, you can have A to the 0. A to the 0 is always E, okay? The epsilon, the empty string, okay? Every time you have some set to the 0, it is just the empty string. It's by definition. Why is it that? Well, when in mathematics you have conventions, it's just because it makes the rest of the system works very well, okay? So it's just a way to have to do less work. So the clean star, we have no S here, there's no space for S's. Clean star is another operation which is defined on the concatenation. So A star is A to the 0, union A to the 1, union A to the 2, okay? Union A to the 3, blah, 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 blah. So can you help me out fitting this? So what's A star? What's in A star? Well, what's A to the 0? The empty string. Okay. So you have to have the empty string. So when you see the star, you know that that set always contains the empty string. Okay. This is important. Remember, bolt it in your memory. Okay. A1. What's A1? No. A1. Remember that A is AB, I think. Yes. So what's A1?
AB.
Exactly. What's A2? Almost. So you have AA, you have BB, but you also have AB and BA. Is that right? So basically, when you see that, this is saying all the possible combinations of the elements in the set. Okay. So you would have, again, BBA, I don't know, ABA, AAA, blah, 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 okay? All the possible combinations of the elements in the system. Now, of course, you have, for example, epsilon A, epsilon B, but it turns out that if you concatenate the empty string with another string, you just get the other string, because the empty string is empty, right? So you have these concatenations, but actually this is just equal to A, this is just equal to B. Okay? This is the empty set. It doesn't contain anything. What's the clean star of the empty set? Does anybody have some intuition? Well, go with the definition, right? I told you that every set to the 0 is just E. epsilon, the empty string. So the clean star of the empty set is just epsilon. Okay. So I don't want to move on until I'm sure that you got this set notation. Okay. We will find it throughout the whole module. So you have to understand it. If there's somebody that doesn't understand it, tell me what doubts you have, so I can explain to you. Okay.
You said there was an E for the empty set. There's also an E that you said belongs.
Sorry?
There was two symbols that look like an E. You said one of them belongs, means belongs. It was when you were showing.
Oh, you're right. Okay.
Scroll up a little bit. That's
yes. So you have two symbols which are actually different. I probably don't write well enough to show the difference. Okay.
Yeah.
So this is the empty string.
Okay.
And this is belongs. Okay. In particular, then we have the other symbols that I use. This means it's a subset. So you use belongs when you have an element that belongs to some set. You use a subset when you have a set, okay? So for example, if I have a set of A, B, C, the subset A, B is a subset of the whole set A, B, C. Is that clear? If you have questions, ask me, because this lecture will more or less dictate how well you will do in your test. So I guess you want to ace it. So I assume there's no questions. Okay. So it's all clear here. Okay, this is the set theory notation that we had a look at, so we can use it later, okay? So where were we? Let's take an overview. Okay, now we can go to the group stuff. Okay, can you read? Can you read it from there? Do you see? No. Okay, thank you. You're shy, guys, huh? You're second year. You shouldn't be shy. I mean, you're paying to take this class. Okay, I guess now you can see, right? So, regular languages. As I told you, the regular languages are a way to describe a problem, okay, and not all problems, but a set of problems that have the same underlying structure. Let's say, informally, that they're quite simple problems, okay? So you can have finite regular languages or infinite regular languages. And so, as I told you, languages are just sets of strings, okay? But they have the property that these strings have some relation with each other. Okay, for example, well, first we have to say all sets of strings which are finite, they are regular languages. So if you can think of a problem which has a finite set of solutions, that you can express with a regular language, okay? For example, can you give me an example of a problem which has a finite set of solutions? Please do. Sorry? Yeah, a lock on a byte, right? You turn the key in, and you have only one solution to the problem. You just turn the key, right? That's a regular language. Okay. Or, well, here I put, for example, the set of stupid passwords. It's finite. And it's composed by password 111, 1234. Actually, there are others, but for the sake of simplicity, I just put these three. So it's finite. You can build a DFA to recognize this language, okay? And you put your string in there, and the DFA accepts if your password is stupid, or rejects if your password is not stupid, okay? And then you have the more interesting problems, the infinite regular languages. So you have a problem, and you have an infinite number of solutions to your problem. Okay? But these solutions have a certain structure, and they belong to the set of regular languages. For example, all strings that end with 0, right? So this you can read now, I guess, no? So every element of X is such that X ends with 0. X is a string, so this is the set of all strings which end with 0. This set is regular, okay? You have an infinite number of solutions. Okay, we're going to make a pause in a minute. So you have an infinite number of solutions, but you can see this problem is quite simple. So you can think about a simple machine that solves this problem, and the simple machine will have the form of a DFA. More about that in a minute. Remember that every language is on an alphabet, okay? Why? Because the language is a set of strings. The string is a concatenation of symbols. So you have to specify the symbols. Okay? If we had, for example, another alphabet, 0, 1, and AB, this set would look completely different. Okay? Another set which is regular, is a regular language, is a set of strings which are composed by zoom. Okay? So you have zoom. Oh, you have the empty string, because here you can have n equal to 0, so 0 and this is empty. You have zoom, you have zoom zoom, you have zoom zoom zoom, and you can build a DFA that tells you, okay, this string is a zoom zoom zoom, or no, zoom zoom zip. Okay. Okay. I hope nobody died today. So I'll just tell you about this and then we make the pause, okay? So, you have regular languages. The regular languages are sets. Okay? You understand that? They're sets of strings. You can build a set of the regular languages. So all languages that are regular can belong to a set. And there's this peculiar property of some set, which is called closure, meaning that when you do some operations on the set, if your final product, okay, of this operation, so you get two sets, for example, you glue them together, you do the union, you get another set. If that set belongs to the superior set, it means that it is closed under some operation. Okay? In this case, under union. Okay, what does it mean? If you get two regular languages and you do the union of them, okay, this set is now a regular language. If you take a regular language, another regular language, and you do the concatenation, so for example, a regular language is string A, a regular language is string B. AB, still a regular language. Okay? For every regular language that you can think of, you can do these operations and still get regular languages. A union B, AB, okay. The clean star of a regular language, still a regular language. Okay? So, now, this I told you about is the underlying structure of a kind of computation that I will show you in a minute. Okay? So, if the solutions to your problem have the property of being regular, you can build a certain machine to do the computation work for you. And you can also use a certain notation to define all the solutions to your problem. You probably know about them. They're the regular expressions. I'm sure that if anybody did some, I don't know, parsing of a website to obtain some information with the software, you had to use regular expressions, right? And regular expressions define exactly the regular languages. So for each regular language, you can express it with a regular expression. 5 minutes of pause. Okay, guys. Okay, we'll wait for the last guys. And then start again. So, what have we done until now? So, what I've done is I presented to you a very practical, pragmatical, semantic problem, and I showed you that this problem can be reduced to a very unmeaningful set of states, transitions, and I gave a name to this graph here, which is a DFA. So what's a DFA? It's a machine. It's a computing machine. Okay. Why are we interested in computing machines? Well, first of all, they have applications in computer science. Okay, so that could be interesting for you. There are software where you can draw these machines, and they get you out. They output the code. Okay, that's nice. For example, if anybody's going to do embedded systems, I think. Well, if anybody's going to program something like a vending machine, right? That's a DFA. That's easily done with a DFA. It's very clear for you to program this way. Just write the DFA down. You get the software. You know, it outputs code. Naturally, you can do it yourself. As I showed you, a DFA is just, you can just implement as a lookup table. And that's exactly what regular languages and these DFA computing machines are about. They solve all problems that can be solved using a finite amount of memory. So if you have a problem, and you can, for example, prove that this problem can be solved with a finite amount of memory, you're sure that you can find a regular language, a regular expression, more regular expressions, some DFAs that solve your problem. Okay, and that's of course really nice. Okay. So I talked about the language metaphor, which we will be using throughout the whole course. So the fact that problems can be seen as languages. So the solutions of your problem are languages. Okay. And of course, depending on your problem, each problem has a different structure, and we learned then that every problem that has a finite number of solutions, or every problem that can be solved with a finite amount of memory, even if it has infinite solutions, is actually as the structure of a regular language. Okay, so it's a set with these characteristics. Okay, how do we define regular languages? Actually, we define regular languages, well, we will be defining here regular languages using the computing machine, which recognizes a regular language, and the regular expression expressing the regular language, okay? Meaning what? Which I won't give you a set theoretic definition of a regular language. I will show you that every regular language comes from a DFA, at least one DFA, and that every regular language can be expressed as a regular expression, so that you will see that's how we define them. Okay, so every language that can be accepted by a DFA, a finite state machine, which is the object I told you about before, if it can be accepted by a DFA, then it's a regular language. Okay, so these three things are related. All right, they're actually talking about the same object. So a DFA, you can just transform a DFA into a regular expression and define with a regular expression a regular language. Or you can, you can take a DFA, you can take a regular expression and make it into a DFA. A DFA accepts only regular language. Okay, they're all defining the same underlying object, the same underlying structure. Okay. So about DFAs. Here I've created the DFA for the language of stupid passwords, okay? And this is the form that every DFA accepting finite languages will have, okay? So, for example, if password is a word in my language, I will just define a path which goes to an accept state, where every transition has a a symbol from the accepting string. Okay, so password PASSWORD accepted. It is a string of stupid. Dragon 89. Okay, we're stuck already. There's no D. Okay. 1 2 3 1 2 3 3 1 1. 1 2 3. No, there's nothing here. It's not accepted. So the only accepted strings here would be the ones from the finite language. And if you have a finite language, you can see it's really straightforward to build a finite state machine. Okay. If you have an infinite language and you know it's regular, you can build a DFA. Okay. For example, I think I defined a language which is the language of all strings on 0 and 1 which ends with 0. Okay? So this is a DFA recognizing exactly that, right? So let's do some input, right? Choose a string. An input string.
0 1 0 1.
0 1 0 1. Okay. 0 1 0 1. Not accepted. Okay? Well, you can see it works, right? 0 1 0 1 0 0 1 0 1 0 accepted. 0 0 0 0 0 accepted. Okay, this is a recursion. So from one state, if you input a 0, you stay there. Okay. 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 Let's build DFAs for the other languages I provided you. So Zoom. Okay. I didn't do it by myself, so I'm prone to errors. If you spot any, just tell me, okay? So Zoom, we want a machine that recognizes Zoom. So of course, Zoom has to be an accepted state. Z, U, M. So if you remember this set, this regular language is the regular language of all the strings that are composed by 0 or more zooms. Zoom, 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 zoom. Okay? So what's missing here?
Perfect.
Thank you. Zoom. And well, we can do like this, right? What letter?
Z.
Z. Okay. So you can.
Also the empty string.
Sorry?
The empty string should be accepted.
You're so right. So
Thank you.
we saw that 0 or more zooms, right? The empty string is 0 zooms. So this is an accept state, the initial state. If we're here, okay, it means we're accepting the empty string. There's no input still. Okay, there's no input yet. So the first state is an accept state. Then as more zooms come in, we move. So zoom is in the language, zoom zoom is in the language, zoom 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 is in the language. Okay, you can see it works. Zam is of course not in the language. Okay. So this DFA, the set of strings that this DFA maps to accept are the strings in a language. Okay. So zoom maps to accept. Zoom zoom accept. Okay. Zam. Reject. What's reject? What does it mean? Everything that is not accept. Okay. If my string is zoom zoom, zoom zoom, this is not an accept state. I'm ending up here, and the DFA is not accepting the string; it's rejecting the string. Okay. So every DFA accepts regular language, and at the same time it defines it, right? Because as I told you, the regular language defined by this DFA is the set of strings that are accepted by the DFA, and it's actually pretty simple. I don't think I have to convince you that this DFA is solving a problem which needs just a finite amount of memory to be solved. You just have to remember that you saw zoom. Then you can forget that what you saw before. Okay, so for each transition as a history, right? If you're here, you know that you receive a Z. If you're here, you know that you receive either a U, no, actually a U, which could be, actually, yeah. If you're here, you know that what you saw is zoo, or possibly some other zooms. Okay, so this machine doesn't really remember much. It's like me when I didn't remember how to order pizza. Okay, at every state, if you trace back the history of every state, you know that every state, for example, ordering. If you ordered, it means that you phoned. Okay, this is the kind of memory I'm talking about. Okay, you don't have infinite memory. Okay? So if you're in a state, well, yeah, you don't have infinite memory. So the class of problems that you solve are those problems that you can solve with finite memory, right? So any other example? I don't think I have some examples hidden here. Regular language, DFA, for example. Okay. Let's do this. I'll give you just another example to make sure that this DFA thing is clear in your mind. Okay. So, B5 is a language on ABC, on the alphabet ABC, and every string which is in LB5 has a length. This is a length operator when you see the two upright pipes. Okay, the length operator gives so x between these two pipes means you're asking for how long the string is. So the length of x is 5. X starts with B. Can we build a DFA to recognize that? Yeah. As you can see, it doesn't take an infinite amount of memory to solve this problem. Okay. You just have to make sure that your string is long 5 symbols, and that the last one is B. You don't need an infinite amount of memory to do that. Okay. So, for example, this is the initial state. Our symbols are ABC. So can you help me out filling this DFA?
That would be empty string.
Sorry?
Empty string would be the first one, wouldn't it?
Sorry, I didn't tell you this. When you have a DFA, this arrow here is just telling you what the initial state here is. You can interpret this as being an empty transition, right? Yeah. But you don't have any state.
Previous state.
Exactly. So, where do we go from the initial state?
B.
B?
Yes, it starts with B.
Right.
And then any4 as well.
Mm-hmm. So it has to start with B, and then any4, meaning what?
Any 4 characters.
Mm-hmm.
So A. And that's C.
We denote it like this, okay? Yeah, I know this is what I thought. I just wanted to. So A, B, C, whatever of these 3. Well, 4. Oh, the length is 5, so B. 1, 2, 3, 4, and 5, and this is exactly. Okay. You see, it's quite straightforward to build these DFAs. Actually, sometimes it is not. Okay. For some problems, you may think, okay, these problems intuitively don't seem regular. It seems like I need an infinite amount of memory. Okay. But just because you think a problem is regular, it doesn't mean it is, non-regular, it doesn't mean it is. It just means that the algorithm you have in mind, it's maybe not the right one. So maybe you can find another algorithm that needs finite memory, which solves your problem. I will show you an example later, okay? But for many problems, it's very straightforward to build a DFA, right? Let's do one more example. So, okay, the language is the set of strings which begin with 0 and with 1, 1, and the length of the string is odd, okay? On the alphabet 0 and 1, okay? So let's do it. Begin with 0. So we know that our first transition has to be 0, and we want an odd number of transitions, okay? So we know this is 1. Oh, it has to end with 1, 1, right?
0, 0.
Sorry?
The next one could be 0, 0, and then 1, 1. That would be.
So let me think. Yeah, we have, okay, to connect these two, right? You see why? Right? Because here, if I come here, then I have just four transitions. But if I add, yeah, every time I do this recursion, I add 2, right? 2 by something plus 3 is odd. Okay, so this is a way to do it. Let's see. Well, 0, 1, 0. Oh no, here I'm using a non-probabilistic machine, right? So 0. I'm missing something. Can you help me out?
Yeah, because you could go 1 and then 0 again, couldn't it?
Sorry?
You could go 1 and instead of going 0, and then it could have 1, 0.
Mm-hmm.
So
exactly. So this one
needs to go
has to
somewhere.
go there, right?
Yeah.
First one or the second one?
The last one.
0.
Yeah, that number 0.
So 0, 0, 1, 1, 0,
Yeah.
1, 1, then it will be even, so it has to be here, right?
But the whole thing could also be 0, 1, 1, which is a free.
0, 1, 1. Oh, no, wait. So if I do this, right? Seems to me it's I'm missing something. So give me a string which is even, and it is accepted here.
0, 1, 1.
0, 1, 1. No, because this is the accept state.
Yeah, but from that, it begins with a 0, ends with 1, 1 is odd, so 0, 1, 1 would be.
0, 1, 1.
So it's not the accept.
0. Oh yeah, sorry. Oh, you're right. I was thinking it was 0, 1, 1. That is right. So what's the problem? Do you have the solution? Are you seeing what I'm missing here? I'm actually solving this live, so and I'm not good at it. I wouldn't pass the test. 0.
You have to get rid of the last circle and
Here?
Yeah, and then the previous one, the accepted state.
Mm-hmm. Well, 0, 1, 1, 0. Oh yeah, I put too many ones, right?
Yeah.
But then here we have a problem because 0, 0, 1 will be
I have to leave the first one with 0. Just loop the first one with a 0 as well on itself.
mm-hmm. 1. So 0, 1. 0,
Yeah, that one needs to loop.
0. Oh, I see what you mean, like this, right?
Yeah.
Okay, 0, But here we have another problem, I see.
No, even, yeah.
Yeah, so we need another state, I think, here, like this. 0, 1.
Yeah.
Huh? Seems solved to me. Okay, but anyway, so you see, sometimes it's not really easy to build a DFA, but it is possible, of course. The only reason why I'm kind of failing is that I have a finite amount of time and intelligence. Okay, so I showed you what the definition of a DFA is. Now I showed you that every DFA recognizes a regular language, and actually the set of regular languages can be defined as a set of languages that are accepted by a DFA, right? What time is it? Okay, we have half an hour. I'll tell you about non-deterministic finite state machines, okay? So this is a really neat result, okay? We have deterministic finite state machines, meaning that at each state, if you input one symbol, you always end up to a certain state, okay? It's deterministic. You know what deterministic is, right? So there's no chance in it, okay? But you can build machines that are not deterministic, right? Now we're in the big thing now is the parallel processing, and this NFAs actually embody the idea of parallel processing. So, for example, this machine here, can you tell me why it is non-deterministic? What's the problem here? Did you manage to find out? Okay, let's say that my string is 0, 1, 1. What happens? No, sorry. Let's say that it is 0, 1, 1 is okay.
Well, where does it go on there first?
Yeah, we have 2 ones, right? So we have 2 transitions for the same state with the same symbol. So which one do we take? We take both, okay? So it's like this non-deterministic finite state machine spans a new process, okay? If we're talking programming, it spans a new process. It creates a new process which runs in parallel, okay? So 0, 1, 1, you will have 0, 1, okay? And then you have the separation of these 2 processes. And then maybe you will have 1, and they will do like that, okay? And actually there's one process that is accepting. So you say that the string is accepted. You see what I mean? Do you have any questions? Okay. So you see, it is a neat model which embodies parallel processing. But the neat fact is it has the same computational powers as DFA, okay? So, yeah, you can span how many processes you want with a non-deterministic finite state machine. Actually, that's not true, not how many you want. It is finite, okay? For a finite number of states, you have a finite number of spanned processes, which could be 1,000 billions, but it's still finite, okay? You can transform this into a finite state machine, into a deterministic finite state machine, meaning that this class of machines compute exactly the same problems as the non-parallel ones. And this actually is it so surprising? I mean, we see it quite a lot, right? You now have quad-core computers, but they're just faster than single-core computers. Okay? I mean, you could run, you could solve exactly the same problems with one single processor than 1,000 ones. So this is a neat result, and the good thing is that some problems are better expressed with DFAs, right? So we talked about closure properties, meaning that if you do the union of two regular languages, the result is a regular language. Okay? If you do the concatenation of two regular languages, the resulting language is a regular language. These closure properties. It is really, really easy to prove them using DFAs. Why proving them using DFAs? Sorry, non-deterministic, so NFAs. Okay? Why would we want to use NFAs? Well, we said that regular languages are the languages recognized by DFAs, and NFAs can be mapped back to DFAs, right? So if you prove these closure properties with NFAs, you prove them for the regular languages, which is nice. Okay. So, for example, the union A union B is a regular language. We can build easily a non-deterministic finite state machine which runs. So A has some machine, okay? Has some machine recognizing it. So let's call it machine A. Then we have machine B. And we just say, okay, if either of them accepts, you end up in an accept state. Okay? These ones are E transitions, these ones, sorry, epsilon transitions. Okay? What does it mean? So you know that A has some DFAs recognizing it. You know that B has some other DFAs recognizing it. Okay? So what you need to do is just span two processes, okay, for your input stream. So when you have the epsilon transition in a non-deterministic finite state machine, it means that you don't have to do anything. If you're here, you're already creating this one. Okay, you see what I mean? So from here, you create two processes. The input string is fed to both processes. If one of them accepts, then accept. Okay, really easy, really clear. Okay, A, B. Can you imagine how this machine will be built? No idea?
Yeah, the machine A, and then after that machine B.
Exactly. So, A and B, E, E, E. Accept. Right? So if this accepts, you go to the initial state of machine B, your string is continuing. If it is accepted by B, you end up in the final state. Do you understand why this is the case? Well, okay, let's do a practical example. Let's say that, simple one. Machine A accepts all strings with a certain number of A's, okay? So accepts A. If you have a string which is made of A's, machine A accepts it. This is the same, but B, okay? You create this new machine. So let's say that my string is A. Okay, A, accepted, but rejected by machine B. Okay? B, rejected by machine A. B. A passes through here. Okay, it is accepted. B passes through here. It is accepted. So it's a concatenation. You see why? So the concatenation of two regular languages is a regular language. You can build an NFA that recognizes it, and from the NFA you can map back to the DFA. I won't explain you how it is. It's just maybe I will explain you the next time. We don't have time today. Concatenation, clean star is even easier. Okay, A. What you have to do is just machine A, and then you see why this is the case, right? So if you have a language, this is accepted. Okay, for example, machine A accepts ABC. Okay, ABC accepted. you have an epsilon transition here, so you're already in the you're again in the initial state. ABC, 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 ABC. Okay, you see, this recursion here makes sure that your machine recognizes the clean start of your language. So that's a neat fact. We proved the closure properties of regular languages just by using NFAs. But again, the computational power is the same for DFAs as it is for NFAs. Actually, I can tell you why. So that's 0, 1, 0. So we have this 0, 1, 0, 1, 1, 2, except 0 and 1. So how do we map back to DFAs? So you see, this is an NFA, right? So you have these two thingy here that don't vary. You span two processes when you go there, right? Well, it's simple. You take count of the processes which were spanned and where they are, okay? So, for example, I start from state 0, and then I can have two inputs, right? 0 and 1. If I am in state 0 and I go with a 0, I actually stay in 0. If I go with a 1, I have two processes. One goes to 0 and one goes to 1, right? 1, I have it here, so I set to 0, the other process goes to 1. Okay, so you have two. You just track them down, and basically you say, okay, 0, 1. You're tracking. You know, the name of the states doesn't really matter. So we name the state 0, 1, because one process now is in 0, the other process is in 1. Okay? So again, if here I have two possibilities, 0 and 1. So if I'm in state 0 and I input 0, I go again to 0 and 1. No, sorry. I state 0 and put 0, I stay in 0.
Should go back.
Exactly, yes, sorry. From state 1, if I do 0, I go to 2. Oh, sorry. It shouldn't go back. It should create another state, right? 0 will go to 0 dot. Why is that? So, if I apply 0 to 0, I stay in 0. If I apply 0 to 1, exactly, I go to 2. Okay? And because one of those states is an accept state, this is an accept state. Really ugly accept state. So 0, 1. If I input 1, I go again to 0 and 1. 0 and 1, but also if I input 1 in 1, I go to 2, so 0, 1, 2. I'm just keeping track of my processes, right? Where they are. Okay. So now 0 and 2, two possibilities, 0, 2. If I go, so if I either input 0 or 1 in 2, nothing happens. So 0, 0 goes to 0 again. 0 applied 1 goes to 0, 1 again. Okay? Zero, 1, 0, 1, 2. 0, 1, 2. So I can apply 0, 1. Okay. So 2, of course, again goes away because there's no transitions. If I apply 0 to 0, I go again in 0. If I apply 0 to 1, 0 to 1, I go to 2. So now it's 0, 2. Perfect. So 0, 0. Apply 1, apply 1. If I apply 1, 0 goes to 0, 1. If I apply 1 to 1, 2, so it is recursive 1. Okay? So as you can see, this is a finite state machine. Okay? And yeah, this is finite, okay? So you have 0, 1, 0, 1. There's no double transition, okay? There's no spanning of other processes. This is really serial. And it accepts exactly the same string as the previous NFA. Now, you can see the advantage of NFAs, right? I mean, this looks really, really ugly and complicated. This one, you read it, you understand what it is doing, right? But it is nice. So if you have to plan, I don't know, if you have to write a parser for a compiler, okay, for the lexical analyzer, you can just do everything with NFAs and then use some software to convert them to DFAs and then that to code, okay? Okay, we have the last 15 minutes. I briefly introduce you to regular expressions. So first, I would like to show you, I'm not sure if I have it. Yes, sir. Oh. You know egrep, right, in Linux? So it's a pattern matching tool, okay? It is extremely optimized, has been around since ages, and what it does is it uses regular expressions to search text, okay? So for example, so you have these conventions here. 0 more occurrences of R. This should remind you of the clean star. This you want an occurrence. Maybe you have R, you don't. Grouping, or okay, you have this, and you can look for strings in text with a regular structure. For example, a problem I may have, right? I'm writing a poem. Roses are red, dogs are red. At poems are sad, but I don't give up. So I have no idea what to put in there, and I could use regular expressions. Now, what did I do? Okay. Don't really remember where I am. Oh, perfect. Okay. So what we want is any word ending with "ak." Okay. This words.txt is just a file of words, and we're going to use our egrep tool to find out. So dot means any character. Then we have the clean star, meaning any character repeated 0 or more times. And then we have ak, which is our word. Right? And words. And it. Oh, I did something wrong. Yeah, I didn't specify that. I just wanted at the end of the word. So I go here, and another symbol is the dollar symbol, which means here the word is finished. Okay, so don't look inside. And now, exactly, we have the words we wanted, right? This is really, regular expressions are really nice if you have to parse a website. A friend of mine built a program in MATLAB downloading the references for a paper. You write your paper, you cite something, and this program looks into your text, takes out the references, and finds out the APA, how do you call it? Reference. No? Yeah. So you cite Giovanni 1998, and it finds with Mendeley Giovanni M, 1998, conference on blah blah blah, robots that love. Okay. Okay, so we found our word here, which is duck. So we can go and complete my fantastic poem. Duck. Oh. So I see you see they're really useful for poems. You can use them for Scrabble and whatever word game you're into. Okay. And the nice thing about regular expressions is they are another way, yet another way to express the same object, which is regular languages. Okay. So a regular expression, you can transform it into a DFA. You can transform it into a regular, well, not transform it. You can define a regular language, okay? So it's really nice. All problems that are regular can be solved using regular expressions, which is not too bad, right? Okay, I'll define them. But yeah, I think that's the last thing we will do today. So you can, again, we find this inductive definition, right? Because regular expressions can be nested, you know, you need an inductive definition because of this recursiveness of the regular expressions. Like the recursiveness we saw with the delta function applied to strings instead of symbols. Okay? So the empty set is a regular expression. Epsilon is a regular expression, the empty string. Every symbol in sigma is a regular expression. What does it mean? That you define regular expressions, of course, on symbols, right? So it depends what your symbol set is. It could be 0, 1. It could be the set of letters from the English alphabet. It could be the symbols that I created for my pizza problem, okay? The important thing is that you have an alphabet. So every single symbol in the alphabet is a regular expression. And then here we do the induction. So if some symbol, if R is a regular expression, then the grouping is a regular expression. Why is that nice? Well, for example, 0, 1, star, right? We want to group, we want the strings that are repetitions of 0, 1s. So empty string, 0, 1s, 0, 0, 1. Sorry, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Okay? So the grouping in it. Clean star, we learned what this is. So if R is a regular expression, clean star R is a regular expression, concatenation, and alternative. So for example, let's use a little bit of those. A plus B star, and we already used 3 of them, and we group with CD. We concatenate with CD. So, can you tell me what this regular expression is expressing? I'll tell you. So it means the first letter of the string is either an A or a B. So you can use plus. I think in egrep you use the pipe. I sometimes use the union because it's coherent with the other notation I use with the sets. So either A or B is the first letter in the string. This is a start. I actually said something wrong because we have this grouping. We have this alternative start, meaning that you can have an A or a B. Then you can have an A or a B. Then you can have an A or a B. So this is all the possible combinations of A and B. Okay? And with the empty string, because it's the clean start. Okay? So all possible combinations or even nothing. Okay? And then CD, concatenated, right? So this means all strings, oh sorry, I didn't define the alphabet, but okay, it is clear. A, B, C, D. Okay? So all the possible strings on A, B, C, D, which end up with CD. Okay? So here, actually that's not true. All the possible strings on A, B, C, D, which in which CD are the last two letters, and they don't appear anywhere before. Okay? Because here you have all the possible combination of A, B, but you don't have a CD anywhere. You have a CD. Okay? So if I were to look for, if I have to look in my list of words for this regular expression that I made up, I don't think we have any words in English with some here in the CD. So I think we will find just CD. CD is a word, right? So we will find CD. Another example, we're running out of time, so I'll just do some examples. This one you will add me, so 0, 1, start plus 0. Okay, can you tell me what regular language this regular expression is defining?
A combination of 0 and 1 with a 0 at the end.
Mm-hmm.
Oh, well, the combination of 0 and 1. 0 and 1.
So, for example, I give you a string and you tell me if it is accepted, okay? If this regular expression captures it. So, 0, 1. Is it accepted? It is in fact accepted because 0, 1 is 1 time 0, 1, okay? So the clean star. Is 0 accepted? But we have the alternative, okay? So it means either this or this is accepted. So this is the regular expression defining strings which are either 0 or 0, 1 concatenated how many times you want, or even empty string, okay? I'll give you one last one and then we can go home. Let's see, A, B, C plus D star. I really have no idea. So, can you tell me what strings I'm defining with this regular expression? Pay attention. There's something you missed.
Any number of these.
Exactly. So these regular expressions define strings which are either A or B or C or any number of D, which could be also 0, so the empty string. Okay? So I think in the next lecture we will do a lot of exercising on this, because you really need to bolt it in your brain, because this structure is the same structure of all the next lectures, okay? I will show you a language, I will show you a machine, okay, which recognizes the language. Also, in the next lecture, I will show you the limits of DFAs, because of course, not all problems require a finite memory, okay? So in the next lecture, I will show you how to see if your problem can be solved with a DFA or not. And what are those problems that cannot? See you next time. Oh, if you have any questions, drop me an email.